In the earlier lectures, we discussed about the polynomial interpolation. So what we did in the polynomial interpolation is we have this set of data points x0 and f0, x1, f1, maybe we have n plus 1 data points, and what we did is we tried to construct the nth degree polynomial which passes through all these n plus 1 data point and use that polynomial to find out the value of the function at some unknown x. The problem with that method is, though it is a very interesting way to get the interpreting the unknown values, many times it fails. The reason is, so for example, if we try to plot the points as these are the points we have. So, and if we wanted to interpolate it, so what happened? And what we are trying to do, we are trying to construct a nth degree polynomial which passes through all the points and use that polynomial to find out the value of function at some unknown x star. So this is our x and this is our f of x or whatever. Okay, so and we use this polynomial to find out the unknown value x. The problem with this type of interpolation, this polynomial type of interpolation is, so to find out this unknown, so since you are constructing a polynomial, the polynomial will have a strong dependence upon all the points you are considered. So the value of the function, what you are estimating here, will have a strong dependence upon the points even far away from the point where you are chosen. So rather than the point here, which far away from the point where you wanted to find out the function, that will have a strong effect on the interpolated value of the function. And when I will show you some demo program, so maybe tomorrow or in the next class I will show you the demo program. There I will show you how this polynomial interpolation can fail in very simpler cases. So it is not, in a way, though most of the time this interpolation works, many cases it won't, and rather there is yet another interesting and a very efficient interpolation algorithm which we call as a spline, which we discussed in our in the introductory lecture on interpolation also. So, and let me repeat it, what do we mean by spline is nothing but a flexible strip. Suppose instead of constructing a polynomial which passes through all the points, I will take a flexible strip, join the flexible strip with the 1, 2, 3 points such that I bend the strip accordingly, maybe some few points are connected, and then I trace the curve over the point, and then I similarly connect these 2 points, and then I keep connecting. So that way I connect all the data points, and from this connected curve I try to find out whatever the unknown value of x star you call that we can use from this one. So the advantage of this method is, since you are connecting using splining over the neighboring points, the effect of faraway points will not be that dominant in the points where you are going to interpolate. So this is an advantage of this spline interpolation, and what we said is a spline interpolation. This is what we call as spline interpolation, the mathematical implementation of this and converting it into a program so that you can use it for any function. So that's what is all about this spline interpolation. So, and this one of the very common, there are many cubic splines and all. One of the very common spline interpolation is the cubic spline. That's what we will discuss today. And there are many other advanced splines also that I leave it to you. You can read it by yourself, and there are p-splines and Bezier splines and all, which are more comes as a fitting procedures. So, and I'm not going into those details. Let us discuss about a simple cubic spline, which is most of the case this is what we need for integrations or something we will see later on. And okay, fine. So what do we do in a cubic spline? So let us see. So what we actually do in a spline is, so we connect first what we are going to do is we will okay, in a cubic spline what does is, so what we are doing, we are taking a strip, this flexible strip, and giving a curvature, and then we are joining the points. In a cubic spline, what it does is that function which you are using to join the points, what we make sure is that function, the second derivative should be continuous up to its second derivative. So that's what is called as a cubic spline. So the curvature, you should give such a curvature that even up to its second derivative has to be continuous. And most of the cases, that's effect. That's more than enough for interpreting most of your data points. And that technique is called as a cubic spline. So let us see how we are going to bring that continuity up to the second derivative. That's what we mean by giving a curvature. So the moment what I said, when I am giving a straight line, when I am giving a curvature, means I am going to, when the straight line only the first derivative remains finite. All the higher derivative goes to 0. So then I want to give a curvature. What I mean by giving a curvature is the higher order derivatives are going to be still finite. So in a cubic spline, you give a curvature such that up to second derivative will remain continuous, and third derivative onwards it will go to 0. It doesn't matter because most of your curves are smooth. For if it is a smooth curve, the second derivative should be means it's a cubic polynomial. Only for a cubic polynomial, the second derivative remains continuous. So, and that's sufficient to most of our cases explain all the smooth curves, unless until if there are sharp spikes are there. Okay, fine. So this is the technique which is going to be used in the cubic spline. So now let us go into how to find the algorithm of this cubic spline. The first step is to connect these points. What am I going to do? Let me do in a very primitive way. I am going to connect these points by a straight line. So I am not going to give any curvature. Let me just use straight line to connect all these points. So let me write down a certain point. Let me call this point as, say, something like xi and fi, and let this be xi plus 1, fi plus 1. So let us take the straight line which is connecting these 2 points. So what will we have? The straight line which is connecting those 2 points, let me call it as f of x. That will be 1 by xi plus 1 minus xi into determinant of x minus xi f of I, x minus xi plus 1 f of I plus 1. So this can be written as, okay, so this can be written as, what we will be write is, okay, x minus xi divided by xi plus 1 minus xi into f of I plus 1 into minus of x minus xi plus 1 divided by xi plus 1 minus xi of f of I. So let me take this minus inside. So this can be written as xi plus 1 minus x divided by xi plus 1 minus xi of f of I plus x minus xi divided by x of I plus 1 minus xi of f of I plus 1. So let me call this function as a of x, because it's a linear function in x, a of x f of I plus, and this is b of x into f of I plus 1. So we are going to write this as, so this equation of the straight line, we can write it as, straight line which is joining these 2 points can be written as a of x f of I plus b of x into f of I plus 1, where a of x is equal to x of I plus 1 minus x divided by x of I plus 1 minus xi, and b of x will be equal to x minus xi divided by x of I plus 1 minus xi. So let us have this function. So what we did is we just connected all these points by a simple straight line. That's a linear function. So and what it says is, so, and that's what we given. We picked up the straight line, we take the spline strip. Now we have to give a curvature. Correct? That's what we want to implement it. Okay, fine. So before that, if you see, so this straight line, if you see the second derivative of the straight line, of course the first derivative will have some finite value. The second derivative becomes 0 because all these functions are just a function in x, and that is not always true. The second derivative becomes 0 only at the intermediate points where you can do a straight line. At the abscissas, where there's a break, the line is breaking, so the second derivative will remain undefined at the abscissas. Only at the intermediate point, the second derivative will be 0. So it is not continuous. What I want to say is the second derivative is not continuous. And now what we are going to do, we are going to give a curvature. This is a straight line, so now I want to give a curvature. So giving a curvature means I am going to add higher order terms in the function what I have. So in a cubic spline, what we do is we add with this f of x, we modify this f of x such that that's a straight line fi plus b of x of f of I plus 1. We add to this term one cubic polynomial, let me call it as phi of x, where phi of x is equal to a cubic polynomial. So it is ax cube plus bx square plus cx plus d. So by adding this polynomial, what I have done is in the straight line, I have given a curvature, which is the curvature is expressed by my cubic polynomial, what I have added to this function. So, and that's how I am going to interpolate it. So I have given the curvature. Now it's not, so I have given, so what the task is now to identify what is my A, B, C and D. Of course, these values are going to depend upon what are the points I am going to take, because I am going to give a curvature accordingly. Fine. So let us how to find out this function. So one simple step I can do is, so if you see here, this f of x, so this is f of x, and if you try to put at x equal to xi, so for example, if you put x equal to xi, so when x becomes xi, a of x becomes 1 and b of xi becomes 0. So when a of I becomes 1, this becomes fi, this becomes 0, so f of x equal to f of I. So f of xi equal to fi, that's what we want. So at the abscissas, this value should go to 0. What I want to say is, so phi of x of I should equal to 0. If it is not 0, then we are not going to get at x equal to xi, we are not going to get f of I, rather this term also, some combination of this term also will come up. So there is a one condition, the polynomial, since the spline function, which I use spline, it should passes through the point. The requirement is this function should go to 0 at the abscissa. So what it gives is, since we are dealing with 2 points, xi and xi plus 1, so then we can write phi of xi, that is equal to axi cube plus bxi square plus cxi plus d should be equal to 0. Let me call this as 1. And similarly, phi of xi plus 1 should be axi plus 1 whole cube plus bxi square plus cxi plus d is equal to 0. Let me call this as 2 equations. So this is the condition we put at the abscissas, my phi of xi should be 0. Now let me think of the second derivative of this function. So let me take, so what will be our f double prime of x? So f double prime of x, so now you see the a of x and b of x are linear functions, linear in x, of course these terms will be vanished. So when f double prime of x, what is the only thing is going to remain is, because of phi of x is a cubic polynomial, so this is the only term is going to survive. So f double prime of x is nothing but phi double prime of x, and that is 6ax square plus 2b. Am I right? Yes. 3ax square, sorry, 6ax plus 2b. So then we can write, so when x is equal to x of I, what we are going to get, this is f double prime of xi, so which I am going to write it as fi double prime should be equal to 6axi plus 2b. And when x is equal to xi plus 1, okay, let me write it as equal to fi double prime, and let me like here as f double prime of x of I. So, and this will be f double prime of x of I plus 1 will be equal to 6axi plus 1 plus 2b equal to f of I plus 1 double prime. And let me call this as 3 and this as 4. Now, so now if you see, basically we got 4 equations, 1, 2, 3, 4, and we have 4 unknowns, 1, 2, 3, 4. In fact, we can solve this equation and find out these unknowns a, b, c, d. Now the question comes is, what am I going to do with the fi double primes? That we will see it later on. For time being, let us see if we know fi's as well as fi double prime is also known, let us assume it. We will see how to get it out. Let us assume fi double prime is also known. So then this is a known quantity. Then we can actually solve for a, b, c, d. So what you have to do, we have to get a and b from here and substitute the a and b here in this equation 1 and 2, and then you can express what is c and d. So I am not going into the detail of this calculation. Rather, I will straight away write. So when you do all this jugglery, so I can replace a, b, c, d, and in fact you can write those things in terms of a of x and b of x itself. So what I will write is the final expression I will write down as, you can do it yourself on your pen and a paper and a pen, you can write down this and do it. So what it will be, your f of x can be modified using these conditions as a of x f of I plus b of x f of I plus 1 plus c of x f double prime of I plus d of x plus f double prime of I plus 1. And what you will see is, I am not going to do this, you can do it by yourself. Yeah, it may take lengthy, but it's doable. It is simple. We have to substitution solve it and solve it the same way what I explained. You can do that, and what you will get is c of x will be equal to 1 by 6 times a of x whole cube minus a of x into xi plus 1 minus xi whole square, and similarly d of x will be equal to 1 by 6 b of x cube minus bx into xi plus 1 minus xi whole square. So this is what the interpolating polynomial. So if the interesting, if somehow if you are able to find out this fi prime and fi double prime and fi plus 1 double prime, or then once if you got it, then that's all, you got interpolating polynomial, because f of x is the one, and because then you put for every unknown x, you find out what is the value of ax using here from the neighboring points, and then you can find out your c of x and d of x, substitute it, and you got the unknown function value for some unknown x. So provided we need to know this second derivative of all those points, we'll come to that later. So this is what the whole thing about this function. So what we heard, so we have somehow used this function is what it mean, we giving a curvature in the points. Okay, and okay, it's why the second derivative should be known. We will see that, because even if I ask you to do it by spline flexible also, you will actually need second derivative. We will see that why, how do we, when we are actually implementing this spline by a flexible strip, how we are estimating this double prime, the same way we can do it here also. So that before that, how we will do it. So let us do some Okay, let me take the first derivative of f of x. So let us say df by dx. So df by dx will be let me write it down, do it here. So df by dx equal to dA by dx into f of I plus dB by dx f of I plus 1, that's for done. Then dC by dx into f. So f of I double prime dC by dx into f of I double prime plus dd by dx into f of I plus 1 double prime. So let us try to find out what is dA by dx. So dA by dx is nothing but minus 1 upon x of I plus 1 minus x of I, that comes from here, and dB by dx is equal to 1 upon x of, so dB by dx is equal to 1 upon x of I plus 1 minus x of I. That's cool. And let us find out what is dCB by dx. So dC by dx is equal to dC by dA into dA by dx. So dC by dA, we are given C is here, dC by dA is equal to 1 by 6 times a square, 3a square minus 1, 3a square minus 1 into xi plus 1 minus xi plus 1 minus xi whole square into dA by dx. dA by dx is equal to minus 1 upon xi plus 1 minus x of I. So this goes off and you can take the minus here outside. So and this square goes off and this is what we get. And similarly dd by dx. dd by dx is equal to dd by dA into dA by dx. Sorry, dB. D is function of b. Sorry. dd by dB into dB by dx, and that will be dd by dB will be equal to 1 by 6 3b square minus 1 into xi plus 1, the same thing, xi plus 1 minus xi whole square into dB by dx is equal to 1 upon xi plus 1 minus xi. So this cancels off. So what we are going to get is, this is what? dd by dx. So therefore, so df by dx will be, let us write it down, df by dB will equal to dA by dx of f of I, dA by dx is equal to minus f of I divided by xi plus 1 minus x of I plus dB by dx is equal to 1. So that will be f of I plus 1 divided by x of I plus 1 minus x of I. I can combine these two and write it as f of I plus 1 minus f of I divided by x of I plus 1 minus x of I. So that's the easier way I can write it. So f of I plus 1 minus f of I divided by x of I plus 1 minus x of I. And then let me go for the next one. dC by dx. dC by dx is equal to minus 3a square minus 1 by 6 into xi plus 1 minus xi times f I double prime plus 3b square minus 1 divided by 6 into xi plus 1 minus xi of fi plus 1 double prime. So this is what our first derivative is. So the interpolating function between the points xi and xi plus 1. So what we have done, till now we are concentrating only between the points xi and xi plus 1. We are not gone anything any other point ahead. So we are just trying to give the curvature, and we gave the curvature is defined by your second derivative. So and this is what we have done. So what we have done is, so we got the interpolating polynomial and the first derivative of the interpolating function we got, and the first derivative of the interpolating function this is one. So let us try to find out the second derivative of the function. If you see second derivative, this will goes to 0. So what you will find is, okay, I don't have to do it actually, it is very straightforward. So the second derivative, d square f by dx square, will be, so this goes to 0, and if you do this, this will become 6a, the same way, this 6a and this 6 is cancelled, so there will be one minus, and okay, what I want to say is something like that. So what it becomes, d square, so this will be what? Let us do this. So this portion, this will be what? So let us take this function as, so we are going to say something like g of x of that is equal to minus 3a square minus 1 by 6 into x of I plus 1 minus x of I. So if you take dg by dx, so that is dg by dA into dA by dx. If you remember, dg by dA will be nothing but minus 6a by 6 into this goes off. So and here it will be xi plus 1 minus xi. If you remember what the dA by dx we got earlier, that is equal to nothing but minus 1 divided by xi plus 1 minus xi. So this cancels off. So and this minus becomes plus. So this becomes a. So therefore, when I take the second derivative of, the whole term becomes a, and similarly you can see this whole term becomes b, and therefore the second derivative will be a times f of I double prime plus b times f of I plus 1 double prime. And this is consistent with our whole whatever the what we are proceeding, because so the whole point is, so now this is at for certain x, okay, so this is for some x. So if I want to find out d square f by dx square at certain x equal to xi, certain abscissas, so what we should get, this should come down to simply f of I double prime. That's what we have done, okay. And if you actually substitute this in the place, when you put a in the place of a, when you put x equal to xi, a becomes 1, and that's why we get f of I double prime. And in the place when you put x equal to xi, this becomes 0. So we got exactly the same. And similarly, you can do it for d square f by dx square of x equal to x of I plus 1. It is trivial. This will become f of I plus 1 double prime. You can substitute here and you will see this is what we get. And so therefore, this second derivative is correct, because at the abscissas, it naturally becomes a second derivative of them, which is what we don't know till now. We have to identify what are the second derivative. Okay, now coming to the important point, how am I going to estimate the second derivative? Because when you want to interpolate the function, the data, what will be given is only xi's and fi's. Of course, the experimenter, whatever, doesn't going to provide you the fi double prime. So now somehow we have to find out the fi double prime and fi plus 1 double prime. If you carefully see in the real event, what am I going to do? We have considered only 2 points, xi and xi plus 1. So now what we do, so now we connected to the straight line with the spline. So now we are giving a curvature. So how much curvature we give such that the curvature we give such that the neighboring points will be connected. Okay, so the point is, so we are giving a curvature such that this point should be connected. So that's the amount of curvature. So what it says is, so and that means this equation, this derivative, this is an important first derivative what we got. So we find out the second derivative such that, so this df by dx, the slope we're calculating from this point to this point at let's say some xi. This df by dx I can calculate at xi using xi minus 1 and xi, or otherwise xi and xi plus 1. So both the derivative at xi, either you calculate from earlier point or the point ahead, they both should match. That's how it gives what is the curvature I have to give. So that gives you an idea about what should be the second derivative. We have to add in our, what should be the second derivative of those points that we can find it out. Let us see. So our aim is to have this df by dx should be continuous over every abscissas. That means either you calculate from these 2 points or these 2 points, they should match. So let us first, this is simple. So we are having, so let us first use the point. I'm going to connect the df by dx. I'm going to estimate from x of I, fi, and x of I plus 1, f of I plus 1, and trying to find out the derivative at xi. So then df by dx at x equal to xi will be, all we have to put is this is okay. So when x equal to xi, the moment when I put x equal to xi, let us come back there. So then what we have, so this is the function. So when x is equal to xi, so this becomes 1. When x equal to xi, a will be equal to 1 and b will be equal to 0. Therefore, df by dx at x is equal to this becomes 0. So a becomes 1. So we are going to get f of I plus 1 minus f of I divided by x of I plus 1 minus x of I and minus a is equal to 1. So of course a equal to 1, so this becomes minus become plus xi plus 1 minus x of I 1 by 6 times. So what should I do is 1/6 of x I plus 1 minus x of I, and here b is 0, so this becomes, and here we have f of I double prime, so b becomes 0, so this becomes minus 1 by 6 times xi plus 1 minus x of I into f of I plus 1 double prime. So a is equal to 1. When a is equal to 1, this becomes 2. Fine. Yeah. Fine. 3 minus 2. So this will become minus. Okay. Fine. So this is what we have. So this becomes 1 by 3 minus 1 by 3, 1 by 3, yeah, that's right, minus 1 by 3 times this. So now we will do it for the next set of point. Let me remove this one. So that is, I am going to find the derivative at xi using this point and this point, that is xi minus 1 comma fi minus 1 and xi comma fi. So in this case our a and b will change, because in the place of xi plus 1 becomes xi and this will become xi minus 1. So in this case, under this case, a of x will become xi minus x divided by xi minus xi minus 1, and b of x will become x minus x of I minus 1 divided by x of I minus xi minus 1. Correct? Yes. Okay. So now, so when we have, so therefore a of xi will be 0 and b of xi will be 1. So then this derivative df by dx at x is equal to xi using these 2 points will be, okay, for here it will be fi minus fi minus fi minus 1 and xi minus xi minus 1. Okay, and this will be minus a is 0, so this becomes plus, and 1 by 6, so this becomes 1 by 6 times xi this will be xi minus xi minus 1. So this changes because we are not using now this point xi and xi plus 1. If you do the same analysis using the point xi minus 1 and xi, this is what the formula we get. Or we have to replace it I plus 1, make it as I, and I replace it as I minus 1, that's what we got. And b is equal to 1, so when b becomes 1, so this becomes 2 by 6 as 1 by 3 plus, oh sorry, I have to write here, this is fi minus 1. This f of I becomes f of I minus 1 double prime, and then plus 1/3, this is 2 by 6 becomes 1/3 of x of I minus x of I minus 1 into f of I plus 1 become f of I double prime. So interestingly, I guess I can remove those things now. Fine. So this is an, so now we can, so let me write this as your, where we have this as A and this as B. So they both should match, they both should be equal. So when we equate them both, so we can actually write, I can straight away write down that equation. So it is trivial just to equate them both, and what will you get is, you can check this one. So xi minus xi minus 1 divided by 6 f of I minus 1 double prime plus xi plus 1 minus xi minus 1 divided by 3 into fi double prime plus xi plus 1 minus xi divided by 6 fi plus 1 double prime. Let me put all this in brackets, that makes it more decent. Okay, so this will be equal to, okay, let me remove this also. So this will be equal to fi plus 1 minus f of I divided by xi plus 1 minus x of I, correct? Yeah, those things come from here, and then minus f of I minus f of I minus 1 divided by x of I into x of I minus 1. Okay. So what we have done is, so we have equated these two, and what we were, the whole unknown what we had is the double primes. So we don't have the double primes, we had to find a double primes. What we did is we equated these two and take all the second derivatives, the unknowns on the left hand side and the known quantities on the right hand side, and that's what gives rise to this equation. So if you can see clearly, there is a I minus 1 double prime is there, and I double prime is of course there, and I plus 1 double prime is also there. And now, so given the set of points, so you have, okay, let me write down the set of points. What we had is x0, x1, x2 up to x of n, f0, f1, f2 up to f of n. So given the set of points, so we know all xi's, fi's, everything is known. So this gives you a system of linear equations in second derivative. Okay, so we can solve this equation. So if for every point, every two points, basically it connects 3 points, I minus 1 and I plus 1. So you have to connect 3 points. Every 3 points will be connected. We can, connecting all three points, we can write down the equation. Okay, so then eventually what happens, we are going to get a system of linear equations in the second derivatives, I minus 1, I and I plus 1. Now if you carefully observe, the number of equations you can construct from this equation is, so let me write it as C. So the number of equations, the linear equations which you can construct from C will be, suppose if you have n plus 1 data, all we can construct is only n minus 1 equations we can find out. Okay, why? You can think it off, because if you want to write down this equation, you start from 0, 1, 2. These 3 will give you one equation, the next 3 will give another equation, next will give another equation. So the n term, since it starts from minus 1, you can see it starts from minus 1 point and the I plus 1 point. So there will be always 2 equations. The first equation, the last equation will not be, these lost quantities cannot be identified. So you can have a matrix of n minus 1 dimension. So okay, the linear equations will be what the equations that can be constructed can be only n minus 1. So if you want to have a look at it, so how will you write it down? You start I minus 1 is 0. When you made I minus 1 is 0, it makes 0. So you'll get equations like from. So when I minus 1 is 0, the first equation will be 0, 1 and 2, because I minus 1 is 0, I is 1 and 2. And second equation, it will be 1, 2 and 3. So, and the third equation will be, okay, so I can go on, 2, 3 and 4. This will be I minus 1, I and I plus 1. This is what I have written. So now, so you can see, suppose if you have 1, 2, 3, 4, 5 points, we are having basically 5 points. So we have, yeah, that will be easier to understand. So I have 5 points, x0, x1, x2, x3, x4 and x5. And we have f0, f1, f2, f3, f4 and f5. So you can clearly see, to form the equation, so first equation can be constructed using x0, f0, x1, f1, x2, f2. And the second equation will be x1, f1, x2, f2 and x3, f3. And the third equation will be x2, f2, x3, f3 and x4, f4. So that's what we have. Okay, one more equations we can form because we have taken 6 points. So x3, f3, x4, f4 and x5, f5. So we basically, for 6 data points, we can construct only 4 equations. For each, we can write down this equation. So that means, but we have, how many unknowns we have? We have 6 unknowns because we want to find out all double primes corresponding to all these values. So but however, this we don't have that many linear equations to find out. So this is what we end up is finally an underdetermined system. Okay, because we don't have as many equations as the unknown. So the one way how to sort it out is, okay, let me write down, let us see how this equation looks in a matrix form. That'd be interesting. Okay, so this equation, when we write to see, so for what I want to mention here is for n plus 1 data set, the equations can be formed will be n minus 1 equations. So this says two unknowns should be assumed. Okay, so let us try to see in the matrix form how this equation looks like. So what we had is, this is the equation in second derivative we got from the from matching the first derivative at every abscissa from the both sides. So if you see, this is nothing but the system of linear equations, and if you write it in the matrix form, this actually involves, suppose if this is the unknown, all the if I write all these unknowns as f1 prime, f2 prime, all those things, as I told you, for n plus 1 data point, we will get only n minus 1 equation. So one value should be already known. Usually what happens is, you assume your we have to have some assumption for the f of 0th second derivative and f of nth second derivative. So in that case, what happens, f0 double prime will become a known quantity. You push it to the right hand side, and similarly when you write down the last equation that will have f of n double prime, you consider that as a that as a known quantity and push it on the right hand side. That's what the right hand side, this first equation will take out your f0 double prime. I have not written the last line. The last one will have this term, f of n, that is x of corresponding 1 by 6 into x of n minus x of n minus 1 into f of n double prime. That will come here. So, and therefore we basically get, for n plus 1 data point, we get only n minus 1 matrix equation, and we can solve for all the f1, all the second derivative of all the points except the f0 and f1 from that by solving this matrix equation. Now if you see, this is again, it's a sparse matrix, it's a tridiagonal matrix. You can see it contains only 3 elements. So what we get is a beautiful tridiagonal matrix. Whatever the earlier classes, whatever you have used a code to solve a tridiagonal matrix, the same code can be used to solve for all these f double primes. And once if you know the f of double primes, then we can find out those so then we can come back to this equation. So once if I know the f of double primes, then we can estimate the function, interpolating function between the points I n I plus 1. So this is how the spline interpolation is being implemented, cubic spline. Now the question comes, what should be your f0 double prime and fn double prime? We said that we have to assume it, right? We have to assume it because of course you can't help it. So there's something called as natural spline. In a natural spline, what they do is, you normally consider f0 double prime is equal to f of n double prime, that's equal to 0. Basically what you're doing, the second derivative of the first and the last point will be actually 0. In fact, if I ask you to do this whole process, not by this method, by giving you a flexible strip, and if I ask you to draw this, if I ask you to do the spline, this is what exactly you will also face, because you have the point something like this, and now when you try to spline it, so all the intermediate points, the previous point will give you an idea what should be the curvature. So all the curvature, previous point will give you the idea of what should be the curvature. Now when you come to the last end point, so you never know what should we don't have a previous point. So you have to start with some curvature. Once you get it, then you can always join those points correspondingly, and similarly to the end also. So this derivative, second derivative at these 2 points, even though if I give you the flexible strip and do, you will have this problem, what should be the curvature I should give for these points, because you don't have another point which is going to decide you what should be the second derivative. So in what we get in mathematically from these equations is consistent with what you have done if I had given you a flexible strip and ask you to spline. So this is how a spline interpolation is cubic spline interpolation is implemented, and you can see now clearly, because what happened, we are all considering, I removed that equation, that final our interpolating function that doesn't bother about the other points far away from it. It all bothers about the neighboring points. The earlier points are used to only to construct your second derivative. What is the curvature you give? But that nothing else, otherwise it doesn't have any dependence. So this will eventually gives you a more smooth curve containing all the points. That's why this spline interpolation, particularly is cubic spline, which is normally when we say spline, what we mean is cubic spline. And that is such a powerful technique to do interpolation compared to a polynomial interpolations. So in the next class, or probably sometimes, we will take a demo and we will see how we will try to we try to interpolate a data using a polynomial interpolation, and then you will see that miserably fails at certain points, and then we will use the same data by interpolating using a cubic spline, and you will see this can fantastically give you the desired results. With that, I stop with this interpolation, the whole interpolation chapter I will stop, and the next class we will look into the next interesting numerical techniques which we will use in our research career. Thank you.